Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 4 and now we're going to focus on the subtopic of 4.3 orbital overlap and hybridization. So we're going to do tutorial question 1, 2 and 3 respectively. So without any further ado, let us start. So for tutorial question 1, we need to use the valence bond theory in order to explain the bonding in HF and show how the bond is formed by the overlapping of the atomic orbital. So in order to do this, we need to know the configuration of the H and F. Okay, so hydrogen, we're going to have one electron. So you're going to focus on 1s1 for the electronic configuration. Meanwhile, for fluorine, it consists of 9 electrons. So the configuration is going to be 1s2, 2s2, and then 2p5. And since we are talking about valence bond theory, so we're going to focus on the valence electron only. So we have 7 valence electrons in the fluorine atom. So we're going to draw the orbital diagram. So for the orbital diagram for the fluorine, which is we're going to focus on 2s2 and then 2p5, going to look something like this. And then we're going to have the orbital diagram for the hydrogen atom, which is 1s1. And then this orbital here and this orbital here, which is a suborbital, and there's orbital here going to overlap together in order to form the bond. So according to the valence bond theory, the covalent HF bond can be formed from the overlap of the 2p orbital. So maybe this one can be 2pz, for example, of the fluorine atom, and then it's going to overlap with 1s of the hydrogen atom. And this overlapping of the orbital will share a common region in space in which the two electrons of the opposite spin forming the covalent HF bond. Okay, and the fluorine atom has one unpaired electron and the hydrogen will also have one unpaired electron. So when they are overlapping, one of them gonna flip the sign and a bond gonna be formed. So the drawing gonna be looking something like this, where the hydrogen gonna have one s orbital, which is one electron, and then we have the 2pz, for example, and we're going to have another electron. So when this orbital here and this orbital here overlap to one another, they're going to be a region of overlapping, and then the electron going to swap the direction. And this is going to create a bond known as a sigma bond because this is a end-to-end overlapping. All right, and as a result, a single bond going to be formed representing a sigma bond. Now for question number 2, what is meant by the term hybridization of atomic orbital? So hybridization means that it is the term applied in order for us to mix the atomic orbital in order to generate a new set of hybrid orbital. Okay, and by understanding this, we can use the electron pair in order to determine the type of hybridization. So the type of hybridization can be sp, sp2, sp3, sp3d, and sp3d2. So it depends on the number of electron pair. So if the number of electron pair is 2, then it's going to be sp. If it is 3, it's going to be sp2. If 4, it's going to be sp3. 5 going to be here, and 6 going to be there. Okay. So for question C, we need to state the type of hybridization of the underlying atom in the following compound. So we have the CH3CH3, which is our ethane. So if we were to expand the structure, it's going to be looking something like this. Okay, so as what you can see in the carbon here, the carbon has 1, 2, 3, 4 electron pair. So when the structure have 4 electron pair, then it's going to adopt a sp3 hybridization. So the carbon-carbon single bond here will achieve a sp3 hybridization at this position. Okay. And then for question number 2, if you were to expand the structure, you're going to get it to be something like this. Okay, so at this carbon here, it's going to have 4 electron pair. So when it have 4 electron pair, then it refers to sp3 hybridization. Meanwhile, the carbon here will have 1, 2, 3 electron pair. So when it has a 3 electron pair, it refers to sp2. Okay, so you can put the S carbon-carbon single bond here referring to sp3, and the carbon-carbon double bond here refers to sp2. And then for the BF3, it's going to be looking something like this. Okay, so the boron here will have 1, 2, 3 electron pair, and when it has 3 electron pair, then it refers to sp2. For CCl4, which is the dichloromethane, tetrachloromethane, so you're going to have a structure of like this. So you're going to have 1, 2, 3, 4 electron pairs, and as a result, it's going to adopt the sp3 hybridization, and the sp3 hybridization will have a tetrahedral arrangement, which is something as what we have drawn. Alright, so now for question 3, we need to describe the hybridization process and determine the geometry of the following species. So for question 3a, we have the beryllium dihydride, and as I mentioned here, in order to describe the hybridization, it is very important for you to be able to draw the Lewis structure according to Vesper. So you need to do the similar process all over again as what you have learned in the previous subtopic, so that the hybridization process can be understood much more clearly. So as usual, you need to find the total number of valence electron first. So the beryllium going to have 2 electron, and then we have 2 hydrogen, which is 2 times 1, which is 2 electron. So the total number of electron that we're going to have is 4 electron. So the beryllium going to be at the center, and it will be connected with 2 hydrogen atom as the terminal. So we have used up 2 and 4. So we have used up all the electrons that we have. Okay, so we're going to get the structure to be like this. And then we need to determine the class of the molecule. So the class of the molecule is going to be A, B, 2, because it has 2 bonding pairs. And this is going to have a structure of linear. So since the class of our molecule is AB2, it means that we have the electron pair to be 2. Okay, and since it have the electron pair to be 2, then our type of hybridization going to be sp. Okay, so by understanding this, you can now describe the hybridization process and draw the hybrid orbital overlapping. So as what you know that you need to draw the orbital diagram for the beryllium for the central atom, as well as the terminal atom, which is the hydrogen. So for the beryllium, it has 4 electron, right? So you're going to have one s2, 2, s2. And since we're just going to focus on the valence electron, so we only look about this. So at the ground state, which is at the stable state, we're going to have 2 electron at the 2s2 orbital. Okay, but as what you look here, the beryllium need to form 2 sigma bond. So what they're going to do is that it need to produce 2 unpaired electron. Mesti menghasilkan 2 electron yang single supaya dia boleh buat bonding. So what they're going to do is that at the excited state, one of the electron here need to be excited to the empty 2p orbital. So at the excited state, 1 electron maintained here, and one of these going to be transferred to the 2p orbital. So at the excited state, they're going to have 2 unpaired electron. Okay, and both of these orbital here is at different energy. So that is why the hybridization state will help you to make the orbital more stable and then make them equivalent in energy. So what we're going to do is we're just going to mix the 2 orbital together, which is one of the s and then one of the 3p. So it's going to become s and p. Alright, so we're going to get 2 single electron for the sp hybrid orbital. Meanwhile, this 2 here is unhybridized. Alright, so what you're going to get at the center here is that you're going to get sp, which is 1 and 2. sp, sp. we have 1 and 2, sp here, and then the other one sp here. So one of the lobe will carry 1 electron, the other lobe will carry 1 electron. Okay. Meanwhile, for the hydrogen, we have two of them together, right? On the right hand side and the left hand side. So the hydrogen will have the configuration of 1s1. So it only has 1 electron. So we just put it here, and then we can put it 2 times because we have 2 of them. So what's going to happen is that, as what you can see, it's going to form a sigma bond on this side. So the hydrogen which has a sigma bond, the hydrogen which has a 1s orbital, okay, put it as 1s, as well as on the left hand side, it's going to have another electron of a different spin which coming from the hydrogen. Similarly goes to this side here, and this region of overlapping is end-to-end overlap, so it's going to form a sigma bond, and here it's going to form a sigma bond. And since the structure here is a linear, then the angle going to be 180 degree. Okay, and all the explanation here is written in this manner to help you to visualize what is happening. Okay, and as what you can see here, our Vesper is consistent with our hybrid orbital overlapping. Now we're going to look into the next question, which is SEF4. So selenium is in group 16, so it have 6 valence electron. And then we have 4 fluorine, so it's going to be 4 times 7, which is 28. So 6 plus 28, we're going to produce 34 electron altogether. So selenium going to be the central atom since it is the most electropositive, and then it is connected with 1, 2, 3, and 4 fluorine atom as their terminal atom. So we have used up 2, 4, 6, and 8 electron. So we're going to get 34 minus 8, it's going to be 26 electron. And this 26 electron will then be used in order to complete their terminal atom first. So we're going to get 1, 2, 3, 4, 5, 6, and then we're going to repeat the process for the other atom. So in order to complete the octet, we have used up 24 electrons, and then we level up with 2 electrons. So these 2 electrons will be placed at the central atom here. So we're going to get the structure to be something like this. And as what you can see, we're going to get the class of the molecule to be AB4 because we have 1, 2, 3, 4 bonding pairs, and then we have 1 lone pair. So it's going to be AB4E. And the AB4E here will have the structure of seesaw, macam jongkang jongkit. So you can draw it to be like this, or you can also draw it to be like this. So basically it is a same thing. So like this or like this is both are acceptable. Okay, but the fluorine here need to be a little bit straight to show that it is a seesaw shape. Okay, so for now I'm just gonna stay in this shape here. Okay, so now when I got a class of AB4E, it means that I got 1 lone pair, right? So I'm going to get 4 plus 1, which is I have 5 electron pair altogether. So when I have 5 electron pair, it means that I will have a hybrid orbital of sp3d. Okay, S1, P3, D1. So 1, 3, 1 means that we have 5 altogether. So this is the easiest method. So the hybrid orbital that I'm going to produce is sp3 hybridization. Okay, and as usual, from your drawing, you need to replicate it in terms of the hybrid orbital overlapping. So you need to know the electronic configuration for the selenium. So selenium will have 34 electrons, and the configuration of its electronic configuration going to be AR 3d10 4s2 4p4. Okay, where AR here refers to 18 electron, or you can also write it in terms of the full hand notation, which is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, I'm just writing it in terms of the full hand notation, which is 1s2, 2s2, 2p6, 3s2, 2p6. Okay, I'm just writing it in terms of the full hand notation, which is 1s2, 2s2, 2p6, 3s2, 2p6. Okay, I'm just use a shorthand notation in order to save space here. Okay, and as what you can see, I'm just going to focus on the valence electron only because the valence electron are involved in the making of bonding. So I have 4s2 and then I have 4p4. 1, 2, 3, and 4. Follow Hans rule. Okay, so from here, I have 2 unpaired electrons. So logically, I can only make 2 sigma bond. However, in my structure here, I have 1, 2, 3, and 4 sigma bond. It means that I need to have 4 unpaired electron. Okay, so sebenarnya I need 4 yang single, tapi I only have 2. So what's going to happen here is that I'm going to excite this electron here to the empty 4d orbital. So when here move to here, what I'm going to get is to be something like this. Okay, so I'm going to have the 2 electron, 1, 1, 1, and 1. So 1, 2, 3, 4 can make 1, 2, 3, 4 sigma bond. Okay, but as usual, the excited state will not have the same energy, and that is why we need to hybridize it. Kita kena make sure that they are in the same energy, and that is why they are getting closer. So they're gonna get 1, 2, 1, 2, 3, and 4. And for 1, 2, 3, 4 here, it is empty 4d orbital that is not involved in the hybridization process. Only this part are involved. Okay, so we are done at the central atom. Now we're going to look at the terminal atom. So for the terminal atom, we're going to have the fluorine, which has a electronic configuration of 1s2, 2s2, and then 2p5. So since it have 9 electrons. So we're going to focus on the valence electron only. So the 2s2 going to be here, and then the 2p5 going to be 1, 2, 3, 4, 5. Okay, so we are focusing on this single electron here. And then you can imagine that we're going to have 4 of those. Okay, so one of these going to attach with here. Another fluorine will make a bonding here. Another fluorine will make a bonding here. And another fluorine will make it here because we have 4. And this 2 electron here is basically representing the lone pair. Dia menunjukkan lone pair dan dia tidak terlibat dalam bonding. Okay, and that is why when we draw our hybrid orbital overlapping, which is sp3, we have 5, right? 1, 2, 3, 4, 5. So sp3d1, sp3d2, sp3d3, the third orbital, sp3d, the fourth orbital, and then sp3d, the fifth orbital. Okay, so we have 1, 2, 3, 4. 1, 2, 3, 4 yang single. Yang manakala one of the orbital will have 2 electron here. Okay, so basically it's up to you where you want to put it, but if you put it this way, it's easier to see. And then it is consistent with our Vesper shape. And then the fluorine, which has a 2p orbital, it's gonna make a bonding with our hybrid orbital at the central atom here. So our central atom going to be Se, and then our terminal atom going to be fluorine. Okay, so fluorine, and then it's going to make a bonding, 1 electron from here. So it has a 2p orbital. So similarly, you're going to draw it for all the sides. Then here, and then similarly goes to here, fluorine, make a bonding here. Here doesn't make any bonding because it represents a lone pair, but here we'll have a bonding. So we're going to label it with sigma bond, sigma bond, sigma bond, and sigma bond. So we have 4. And as what you can see, our hybrid orbital overlap will be similar to the Vesper shape that we have drawn. Okay. Now for question G, we have ICl2-. So as usual, we need to calculate the total number of valence electron first. So iodine is in group 17, so we have 7 valence electron. And then we have 2 chlorine, so 2 times 7, 14. And then it have a negative charge. So it means that it received 1 electron. So we're going to plus with 1 electron. So the total number of electrons that we're going to have is 22 electrons. So now we're going to draw the Lewis structure. So between I and Cl, I is more electropositive. So I going to be the central atom. And then it is connected with 2 chlorine. So 2 and 2 here, so minus 4. And then we're going to left with 18 electron. This 18 electron is going to be used in order to complete the octet for the terminal atom first. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have used up 12 electrons. So the balance is 6 electrons. The 6 electrons will be used in order to complete the octet at the central atom. So we're going to place it at the central. 1, 2, 3, 4, 5, 6. Okay. And this is the structure that we're going to having. And it's going to carry a negative charge because the polyatomic ion will have a negative charge, and this is proven when you calculate the formal charge. So for the formal charge of chlorine, so formal charge can be calculated by valence electron minus lone pair electron minus the bonding pair. So for the chlorine, it has 7 valence electron minus 1, 2, 3, 4, 5, 6 lone pair electron minus 1 bonding pair. So it's going to be 0. So 0 here and 0 here because it is identical. But for the iodine, we're going to have 7 valence electron. And then we have 1, 2, 3, 4, 5, 6. 6 lone pair electron. And then it have 1 and 2 bonding pair. So it's going to be minus 1. So it's going to have a charge of minus 1. So that is why the summation of formal charge in which we add 0, negative 1 and 0, it's going to have a negative 1 charge. So negative 1 here is consistent with the negative here. Okay, so we know that this is a correct structure. And then we're going to determine the class of the molecule in order to determine the shape as well as the type of hybridization. So in this case, we have A, which is the central atom, and then it have 1 and 2 bonding pair. So it's going to be AB2. And then for lone pair electron, we're going to have 1, 2, and 3. So it's going to be AB2E3. And this AB2E3 here will have a linear shape, okay, according to the Vesper table as what you have learned. And then since it have 5 electron pairs, okay, so 5 electron pairs here refers to the type of hybridization to be sp3d. Okay, and now from your understanding from Vesper, you need to draw the hybrid orbital overlapping. So it is consistent to what your Vesper drawing here. So as usual, we need to look into the electronic configuration of iodine first. Okay, and remember, because iodine has a charge of -1, and that is why we need to include the -1 in our electronic configuration. So here, we know that iodine will have 53 electrons, but we need to plus 1. So the total number of electrons that it have is 54 electrons. Okay, 53 kalau iodine to neutral, tetapi kita tengah cakap I minus. Maksudnya dia menerima, so total we're going to be 54. And then in the neutral state, you're going to have 5s2, 5p5. Tetapi bila dah terima lagi satu, it's going to be 5s2, 5p6. So we're going to look at the valence electron only. So 1, 2, 3, 4, 5. And then 1, 2, 3. So we have 5s2 and then 5p6. Okay, but as what you can see here, it need to form 2 sigma bond. So logically, it needs to have 2 unpaired electron. So what they're going to do here is that they're going to excite 1 electron to the empty 5d orbital. So what going to happen here is that one of the electrons here are going to be excited there, and as a result, we're going to produce 2 unpaired electrons in order to make 2 sigma bond. And as mentioned, the excited state will not have a similar energy. So what's going to happen here is that we're going to hybrid them together. So we have S, and then we have 3p orbital, 1, 2, 3. So it's going to be sp3, and then 1d orbital, sp3d1. So normally number 1 here is ignored. All right. So what we're going to get at the end is like this. Okay. So if we were to draw the structure, which is iodine minus here, and then we're going to have sp3d1, sp3d2, sp3d3, sp3d4, and then sp3d5. It have 1, 2, 3, 4, 5, and that is why we have 5 lobes. Okay, 5 kelopak. Okay, we put it as sp3d, sp3d, and then sp3d. Alright, and as what you can see here, the two of the lobe, dua kelopak tadi tu akan ada satu elektron sini dan satu elektron sini. The others gonna have 2 electron each. Okay, kat sini. Alright, and this 2 unpaired electron here will make a bonding with the terminal atom, which is chlorine. So chlorine will have a configuration of 1s2, 2s2, 2p6, 3s2, and then 3p5, because chlorine have 17 valence electron. So we're going to focus on the valence electron only. So we're going to get 3s2, and then 3p5 going to be 1, 2, 3, 4, and 5. Okay, and then we have 2 of them. So one going to produce sigma bond here, another orbital will form a sigma bond here. So it will join at the left hand side, chlorine, 3p, 1 electron from here, and then similarly on the right hand side, chlorine, 3p, another electron. And then this end-to-end overlapping here will form a sigma bond, and then this will form a sigma bond. And we need to put a bracket at the end to show that it carries a negative charge consistent to what we have drawn in our Vesper. Okay, and we're going to get a linear shape with an angle of 180 degrees. So what we have drawn in our hybrid orbital overlap is the same as our Vesper molecule. Okay, but for this case, you need to be careful of the negative sign, and that only you can make the structure consistent. Okay, so I think that's all for today's video. See you again some other time. Bye.